Alright, so here I want to talk about strain and vorticity. So these are the two topics I'll be covering in this in this video. So, what are the strain and vorticity? Well, there are grid, or velocity grid can be broken into two pieces. One is a deformation, which is the strain, and the second one is a solid body rotation, which is the vorticity. So two different, very different things. I mean, related, but still quite different. So before I give you the math, I wanna give an example. So imagine we have a Ferris wheel. So we have our circle, and then we have our little cards around it. So if we imagine our Ferris wheel to just go around the way it is, un unlike a Ferris wheel, technically speaking, because at a point two, the uh, squares will not move. They will stay in the same exact direction. Actually, sorry. Uh, you know what? Let's start with the real Ferris wheel. So when they move, this Ferris wheel will have these boxes. Oops, that's not what it. Will have these boxes remain the same direction and turn around. But as you can see, these boxes are not fixed to the outside. They are rotating around. Because if this is the part that points towards the bottom, at a different time, simple, over here, sorry, towards the center, over here, that arrow there is not pointing towards the center anymore. Here is not pointing towards the center anymore. Here is not pointing towards the center anymore. Here is pointing towards the center. But when it moves, the face is not facing the center anymore. This is strain. We're actually moving. We're actually changing um uh the Ferris wheel. We're deforming it. So if you imagine, we have a box over here, and then after a while, the box is something like this. Sorry, because we applied a force like this over here and a force like this over here. This is a strain. We're changing quite like kind of like the shape of the object itself. But if instead we have vorticity, then in our Ferris wheel, we have our box with this face center looking towards center. Then when as this box moves, it also starts to rotate. So it becomes like this. After a while, imagine these are different times. This after a while, and this after a while. Now, if you were in the Ferris wheel and this were real, here you would be upside down. So that's not how Ferris wheel works. But instead, if you imagine a box, then after a while, the box will simply be like this. It is still a body. So, for example, it's rotating in this direction, I would say. It's still a body. It's still solid because it's the same shape, but it's rotating. So that's the difference between strain and vorticity, very simply. And we can look at it for under the math, and we can say that du I over dxj is equals to 1/2 of our du I over dxj plus du I over dx, sorry, duj over dxi plus 1/2 du I dxj minus du I over dx duj over dxi. Now this is both the strain and the vorticity. The first one here is the vorticity, sorry, the strain, and we have to say it is symmetric. It is symmetric matrix, and then this one is the vorticity, and it is anti-symmetric. Um, these are the two uh, things, and if we were instead to go from the velocity, we can say it's the curl of our velocity vector, and we get a uh, vorticity vector. We can also write it in Einstein notation, which is this ijk d u j dxi. And this, you have to remember the components of our uh, vorticity vector will be uh, the the vorticity magnitude is twice the angular velocity, because here we divide it in fact by 2. So that is all you need. You can build a tensor of these two also. Another way you can write this is by saying that uh, the first one is a S for strain, I, J, and then the vorticity has a sigma. I think that's the name of the symbol. I, J. And this is really all you need to know about the uh, vector, about this vorticity and strain. You can also build this with our vorticity vector, of course the vorticity, and it will just be, I should do it, I, j is equals to, we have zeros along the x and y because these parts here will be the same. And then we have negative 1/2 omega z, 1/2 omega y, negative 1/2 omega x, 1/2 omega x, negative 1/2 omega y, and then 1/2 omega z. As you can see, it is antisymmetric, means that if we were to transpose it, this would just be the negative of this, or it would just be the negative of j I.